Thank you guys for coming to this session. My name is Qihui Zhao. I'm from China Mobile. And before I start the session, I want to ask a simple question. So I know that the NVIDIA is almost the most popular GPU on this planet or maybe in the universe. And how many of you are still using something else like Intel or AMD? Oh, good, only one. Okay, I know it's popular, but I didn't expect it's this popular. So I think there's some reason you come to my session. You may still have a teeny tiny thoughts about running your application on some other accelerators, and this is the session. We are creating a software stack to enable your AI tasks to run on any AI infrastructure. When talking about the AI infrastructure, we usually care more about the higher performance of the hardware, the higher bandwidth of the hardware, and the greater scale of the hardware. But the hardware thing is not everything. We know that if we refers to the ecology of the cell phones, the hardware only depends on one part of the ecology of the system. The software stack is another important part. And for example, the BlackBerry, the iOS, the Android, the more open the software is, the more user-friendly the software is, the stronger the developer ecosystem it will have. And that's why the Android engaged like 70% of the overall global market. And this is the same to the NVIDIA CUDA. And we know that CUDA has magnificent development tools. It has tens of thousands of computing libraries and connected libraries. And also it provides very, very flexible platform interfaces. And with all these great software stacks, it gained over 5 million developers all over the world. And that's why the NVIDIA GPU is so successful. And it has a great software stack ecology, and it gains it a great GPU market share. And although the software ecology is important, the users are still choosing heterogeneous hardwares because they have different requirements. For example, for some science, they want to do their algorithm on GPUs, on CPUs. They will choose the some general computing capabilities like CPU. And for some game designers, they will choose GPU. And for some deep learning or neuroscientists, they will choose the domain-specific cards. And also for some of our customers, they prefer higher performance and wanting to pay the higher price for that, they will choose better cards. And for some of our customers, they want to cares more about the cost, they will choose the cheaper hardware with lower performance. So this makes it common that we will have and continuously have the heterogeneous AI cars in this world. And also, if we look at the Meta, Microsoft, they're even designing the accelerator hardware with CPU, NPU, and custom engine. And these cars are born to be heterogeneous. So the heterogeneous accelerator is common. And also for our operators like China Mobile, and also even for cloud providers like Alibaba, we usually have at least 2 types of accelerators existing in our data center, and that gives us some question about how can we use the different accelerators together, and how can we collaborate them together. And here we think that to use the heterogeneous AI hardware, the best way is to have an standard operating systems just like Android. It can get all the hardwares plugged into the operating system and allows the applications to be developed over the operating system without knowing the underlying difference about the hardware. And but the Android for the intelligent computing system hasn't existed yet. And currently, the accelerator manufacturers are trying to build their software stack, including the compiler, runtime, compute libraries, and frameworks based on their hardware architecture. And for this, we call it the silos of AI framework and tool chain and hardware. And the silos cause a lot of problems. For example, for the application developers, if they want to move their application from CUDA to ROCm, for the best situation, they only need to rewrite all the APIs, change the CUDA API to ROCm API. But what if there's no implementation of the ROCm API, which is corresponding to the CUDA API? They have to rewrite the whole code for that part. And that's huge work for the application developers. And also, the silos cause problems for the operators and the cloud service providers on the resource planning and also the utilization rate. Because when we buy heterogeneous hardware, some of them are popular and some of them are not that popular. And for those non-popular hardwares, we usually receive very, very low utilization rate. And also this causes problems for us to do the resource planning. It put us into a dilemma. For example, if we want to gain more customers, we have to buy the diverse hardwares. And if we but that will give us a problem about the low utilization rate. But if we want to only buy the most popular hardwares, we will lose some of our customers. So that is the problem for the operators and the CSPs. And for some new manufacturers about the hardware, if they created a new hardware, they have only two options to gain their ecology. One is to follow NVIDIA ecosystem. They make their APIs just like the NVIDIA ones. Another one is that they create their new one, but they're facing the problems about how can we get more customers for their own manufactured accelerators. So this is the problems that are caused by the silos, and we think that the siloed intelligent computing system ecosystems will restrict the synergy of the heterogeneous accelerators. And for us, we think to provide the flexibility of the intelligent computing systems, the easiest way is to build a Android-like toolchain, and that's what China Mobile is doing right now. We're creating a toolchain named Kama for the heterogeneous accelerators. The whole name for Kama is cross-architecture migrating application, and we just added a layer between the framework layer and the hardware layer. It can help to shield the difference of the of different hardwares and also of different hardware-related tool chains. And the goal of this the software stack is to achieve the AI tasks flexibly executed and migrated over multi-vendor and multi-types accelerators. And one thing to mention here is that with this, our goal here is not to let you rewrite the code and to do the migration. We want to give you a solution that you only need to write the code once and compile the code once, and then you can run your application everywhere. Okay, and let's see that how we implement this. So the core idea of Kama is to build a unified and abstracted hardware model for heterogeneous accelerators. And also, we define a group of standard runtime interfaces for those hardware accelerators. And this refers to the key technology number 3 here and number 4 here. the computing resource abstraction and adaptive runtime. And with these two technology, we can just inject all the hardware and the hardware tool chains into this adaptive runtime and shield all the difference from the adaptive runtime layer. And this adaptive runtime doesn't replace any of the runtime of the original runtime of the hardwares. And then this is the bottom. And to the users from the top, we have defined a unified programming model. It gives the developers an opportunity to write a single source code over heterogeneous hardwares. And with that, we have a single entrance from the top, which is one piece of application code. And with the layer 2 capabilities, we have multiple access at the bottom, which are the heterogeneous hardwares and heterogeneous runtimes. And the only left question is how to link them together. So for us, we have figured out the key technology number 2, the cross-architecture compilation and the optimization. So we will take the single source application source code and get them compiled to a standard format. It's a standard intermediate representation, which we call it a native program. And this native program will be like flow to any hardware and the runtime environments and be recognized, be illustrated, and be linked on different runtime by the adaptive runtime, and then it can be executed. So that's almost that is the whole process for the Kama technology. And one thing we want to mention here is that maybe someone would say, you can do it just using PyTorch or just using TensorFlow. Yes, and we think that doing the cross-architecture implementation at the framework level is easy. We can just simply define some framework level APIs and to like do the adaptation of the vendor specific framework to the standard APIs, and that's it. But we also think that the framework APIs and the corresponding functional implementation are highly related to the use cases. So how many use cases do we have for the AIs, the game, the education, the manufacturing, the deep learning? A lot, right? And how many APIs and functional implements we have to do for them? I think it's countless, and the number of the implementation and the APIs will keep increasing. And so if we want to do the cross-architecture implementation at the framework level, we will have to like do the adaptation for tens of thousands of APIs here. And if we want to do the cross-architecture over multiple hardwares, the total number will like multiply the number of types of accelerators to do the final math. So that's a huge work. And also doing the cross-architecture implementation at the framework level cannot give you the capability to actually write your own code over heterogeneous accelerators, because all the framework like PyTorch or TensorFlow, they are supported by some backend like the computing libraries like Qdnn or Kubernetes. And if we don't have implementations in that, you still need to write your own code with CUDA or ROCm or anything else. So that is the whole idea for us. We will do the cross-architecture implementation at the toolchain level and gives you the capabilities to like code once, build once, and adaptively run on any heterogeneous accelerators. And here are some details about all the key technologies. The first one is computing resource abstraction. For this abstraction, we followed the OpenCL model to abstract the entire hardware, which includes the abstraction of the device model, which includes the host side and multiple device side. And the memory model, the host memory, global memory, local memory, private memory. It's just like any GPU or any DSA would have within their hardware architecture. And also we will have a unified execution model, which defines the structure of the compute unit and how we load the kernels from the host to device through the command group or some command queues here. And this is the abstraction of the heterogeneous compute resources. And someone may ask, if you are using OpenCL, what is the new for your design? Here we have this make some upgrades here. For example, the OpenCL will defines the kernels to be launched from host to device as the smallest unit. But for us, we have upgraded that. We are taking the graph, or maybe we call it the tasks, to be launched from host to device, and each task will contains one or more highly related kernels. And this is one improvement. And another improvement is that the OpenCL model still gives you the layered memory structure. But for us, we have created a unified, shared, and centralized memory zone. And you can directly put your data into this memory zone, and without indicating that where you want to put them. You can just nominate the data you want, and it will directly transfer to the location that you want to use it. So that's about the computing resource abstraction. And key technology number 2 is the adaptive runtime. Like we mentioned before, the adaptive runtime defines a group of abstracted standard APIs. And these APIs are used to operate the abstracted computing resource. For example, init an abstracted device and do the memory copy between the host and device and launch kernel on different devices. And this common, right? But what's new here is that our adaptive runtime is not just a runtime to do the load and link things. We are a runtime system that we can manage all the runtimes of for example, Intel, the AMD, the NVIDIA. When we have the native program mentioned before, loaded to the whole system, the adaptive runtime will adaptively load the IR, the highly related IR about the hardware within the native program, and adaptively link the native program to the device runtime and to do the final execution. So this is about the adaptive runtime. And another key technology is the unified programming model. So for the unified programming model, we have to say it is just a SQL and can support the developers to write the single source code for their application over heterogeneous accelerators. So you don't need to using C++ to write the host code and switch to CUDA or RAWCOM to write the device code. And you can directly write them like here, the parallel 4. You can have all the computing things right here and launch to the different devices. So that's about the unified programming model. And besides the model here, we also define a tool to help to translate CUDA to SQL, and this will give the application with some cross-architecture feature to at the source code level. And the last key technology is cross-architecture compilation. This is one of the most important key technologies that we have in the whole system. So it refers to the LLVM and MLIR. We are trying to build a strategy among the cross-architecture compiler as well as the backend of the accelerator-specific compilers. So the workflow of the whole system is that the cross-architecture compiler frontend will take the unified programming model first and recognize the parallel task within the applications. And then it will send the host part just to GCC to do the normal compilation. And all the parallel tasks will be lowered to some standard dialect. And this dialect will be given to the accelerator-specific compilers to do the final compilation. And that would be the binary code for all the different accelerators. And then after the compilation, we will combine or group all the compiled binary codes together into one executable file. And this follows this executable file is the native program we mentioned before, and it follows the ELF structure. So that's all about the cross-architecture compilation. And for now, following the key technologies that China Mobile has been building a platform named Qihui. And by naming it Qihui, we mean that we want to merge and group all the accelerators together and to use them together. And currently, the platform has 4 major functional components, which are unified programming suites, which gives you the compiler, the IDE, the debugger for you to do one-station development about your application, and source-to-source conversion tools, which helps you to transfer from Kubernetes to SQL, and cross-architecture compiler, and adaptive runtime. So these are the 4 major components, and besides this, we are still creating the high-performance computing libraries as well as the inference engine to adapt our system to the to help them to gain better performance and as well as to connect with the PyTorch. So that's the situation about our implementation about the technology. And for now, the whole platform has been adapted to 8 types of AI accelerators. We can do one type development and singly migrate your applications, live migration of your applications over these 8 types of AI accelerators, which includes NVIDIA, Intel, AMD, Accent, and also some other Chinese chips. And also the live migration time would be less than 20 seconds. And the translation rate of the source-to-source conversion tools would be over 95%. So that's all about the Qihui platform. And finally, now we are planning to open source the whole Qihui platform under OIF CFN working group. And for now, we just only open source some part of it, which are the adaptive runtime interfaces and the NVIDIA CUDA backend. And the source code of the compiler and runtime would be open sourced maybe later this year or maybe earlier next year. So that's pretty much all about the session, and thank you for your time.